The velocity of 3I/ATLAS defied comprehension. At 130,000 miles per hour, it was moving faster than any solar system object ever recorded. This wasn't just impressive, it was unprecedented. The speed told us something crucial about where this visitor had been and how it got here. To understand this velocity, we need context. The Earth orbits the Sun at about 67,000 miles per hour. That seems fast, but it's only half of 3I/ATLAS's speed. The Voyager 1 spacecraft, humanity's fastest object leaving the solar system, travels at 38,000 miles per hour. 3I/ATLAS was moving more than 3 times faster. This visitor was in a cosmic hurry. The extreme speed created immediate challenges for observers. Telescopes had to track the object constantly. It moved across the sky so quickly that long exposures were impossible. Imagine trying to photograph a race car with a camera meant for portraits. The technical demands pushed our equipment to its limits. But speed also tells a story. Objects don't achieve such velocities by accident. Something powerful accelerated 3I/ATLAS long ago. Perhaps it was ejected from its home system by a close encounter with a giant planet. Or maybe it gained speed through multiple gravitational assists over millions of years. Each possibility revealed different formation scenarios. Compare this to our previous interstellar visitors. Oumuamua traveled at about 59,000 miles per hour when discovered. That was shocking at the time. Borisov moved at 76,000 miles per hour, also impressive. But 3I/ATLAS nearly doubled Oumuamua's speed. The progression was puzzling. Why were these objects getting faster? One explanation involves detection bias. Faster objects spend less time in our solar system. We can only detect them when they're close and bright. Perhaps there are many slow interstellar objects we simply haven't found yet. The ones we see might be statistical outliers, the speed demons of the interstellar population. The velocity also affected what we could learn. 3I/ATLAS would remain observable for only about 8 months. After that, it would be too distant and faint. Compare that to regular comets that orbit for years or decades. We had one shot to study this visitor. There would be no second chances. The physics of such speed is remarkable. To reach 130,000 miles per hour requires enormous energy. If 3I/ATLAS started from rest in another star system, the ejection mechanism must have been violent. Giant planets can act like gravitational slingshots, but even Jupiter would struggle to accelerate something to this speed. The process probably involved multiple encounters or an unusually massive planet. Scientists calculated the trajectory backwards, trying to trace 3I/ATLAS to its origin. But at such speeds, the object could have traveled hundreds of light years. Over millions of years, gravitational encounters with other stars would have altered its path. Finding its home system was like tracking a bullet back to the gun after it had ricocheted off 1,000 walls. The speed record raised profound questions about the interstellar environment. If objects this fast are common, space between stars must be filled with high-velocity debris. Each piece carries kinetic energy equivalent to massive explosions. The galaxy becomes a shooting gallery of cosmic projectiles. For 3I/ATLAS, speed was both a blessing and a curse. It brought this messenger to us from impossible distances, but it also guaranteed a brief encounter. We were watching the fastest natural object ever to visit our solar system, and it was already racing toward the exit. The detection of 3I/ATLAS triggered the most coordinated astronomical response in history. Within 24 hours, telescopes on 7 continents and in space had joined the observation campaign. This wasn't planned. There was no protocol. The global astronomy community simply understood that this opportunity wouldn't come again. The Hubble Space Telescope received emergency target status. Normal observations were postponed. The telescope's handlers redirected it toward 3I/ATLAS within 48 hours of discovery. This kind of rapid response usually requires months of planning. For 3 I/ATLAS, normal rules didn't apply. On the ground, major observatories cleared their schedules. The Very Large Telescope in Chile suspended routine observations. The Keck Observatory in Hawaii redirected its twin 10-meter mirrors. The Gemini North and South telescopes coordinated to provide continuous coverage. Each facility brought unique capabilities to the campaign. The James Webb Space Telescope faced a particular challenge. Its observation schedule is planned years in advance. Every minute of time is precious. But 3I/ATLAS demanded immediate attention. Controllers worked around the clock to find observation windows. They squeezed the visitor into gaps between other programs. The infrared data would prove crucial for understanding its composition. Coordination happened through informal networks. Astronomers shared data in real time through online platforms. Preliminary results posted to archives became available worldwide within hours. Traditional publication timelines, usually months or years, compressed to days. Science was happening at internet speed. The International Astronomical Union served as a central clearinghouse. They collected positional measurements from observatories worldwide. Each observation refined the orbital calculation. Within a week, the trajectory was known to extraordinary precision. We knew exactly where 3I/ATLAS would be months in advance. Radio telescopes joined the effort, searching for unusual emissions. The Very Large Array in New Mexico, the Arecibo Observatory in Puerto Rico, and FAST in China all monitored the visitor. They found no artificial signals, but the search itself demonstrated our capability for rapid response. Amateur astronomers contributed valuable observations. While 3I/ATLAS was too faint for small telescopes to study in detail, skilled amateurs could track its position. Their measurements helped fill gaps when professional observatories were weathered out or committed elsewhere. This citizen science approach distributed the workload across thousands of volunteers. The European Space Agency coordinated space-based assets. Beyond Hubble and Webb, smaller telescopes contributed specialized observations. The Swift Observatory studied ultraviolet emissions. The Transiting Exoplanet Survey satellite provided continuous photometry. Each instrument added unique data to the growing archive. NASA established a dedicated 3I/ATLAS working group. Scientists from different missions shared findings daily. The Mars Reconnaissance Orbiter team prepared for the October flyby. The Juno team at Jupiter explored possible trajectory modifications. Even missions not designed for comet science considered how they might contribute. The data flow was staggering. Terabytes of observations accumulated weekly. Machine learning algorithms helped process the information. Patterns too subtle for human eyes emerged from computational analysis. The global response wasn't just about collecting data. It was about making sense of an overwhelming amount of information. International cooperation transcended political boundaries. Scientists in countries with tense relationships shared data freely. The visitor from another star system made earthly conflicts seem petty. For a brief moment, humanity's scientific community united around a common goal. This coordination happened without formal treaties or agreements. It emerged organically from shared scientific curiosity. The response to 3I/ATLAS proved that when faced with genuine cosmic mysteries, we can work together. The visitor brought out the best in human scientific collaboration. Before 3I/ATLAS surprised us, we thought we understood interstellar comets. Comet Borisov had visited in 2019, and it behaved exactly as predicted. It looked like our solar system's comets. It acted like them too. Scientists felt confident about what the next visitor would bring. Borisov had been reassuring in its normalcy. It developed a typical coma as it approached the sun. Its tail pointed away from our star, pushed by radiation pressure. The spectrum showed familiar molecules: water, carbon monoxide, and various organic compounds. It was like meeting a foreign tourist who spoke our language perfectly. The textbooks seemed clear on comet behavior. As these dirty snowballs approach the sun, their ice turns to gas. Water dominates the emissions. making up 80 to 95% of the vapor. Carbon dioxide and carbon monoxide contribute smaller amounts. Dust gets carried along, creating the visible tail. This pattern held for hundreds of observed comets. We expected 3 I/ATLAS to follow this template. Why wouldn't it? The laws of physics are universal. Ice is ice, whether it forms around our sun or another star. Temperature and pressure work the same way everywhere. Sublimation, the process of ice turning directly to gas, shouldn't depend on which star system you're from. The confidence came from good reasoning. Stars like our sun are common in the galaxy. They should create similar planetary systems with similar chemistry. The basic ingredients are the same everywhere: hydrogen, helium, carbon, nitrogen, oxygen. These elements combine in predictable ways. We expected familiar molecules in familiar proportions. Our models predicted the activation distance too. Comets typically turn on around 3 astronomical units from the sun. That's where water ice begins sublimating significantly. 3 I/ATLAS was discovered at 4.5 astronomical units, so we expected to watch it wake up. The activation process should be gradual and predictable. Scientists prepared observation campaigns based on these expectations. They allocated telescope time for water vapor studies. They planned to measure the water production rate. This would tell us about ice content and thermal properties. Standard comet science applied to an interstellar visitor. The spectroscopic teams focused on the usual suspects. They configured their instruments to detect water, carbon monoxide, methane, and ammonia. These molecules appear in most comets. Their relative abundances vary, but water always dominates. It's the most common ice in the solar system. We also expected normal outgassing patterns. The sun-facing side should be most active. Material should flow away from the heat source. The tail should point directly away from the sun. These geometric patterns result from simple physics. Heat causes sublimation. Radiation pressure pushes gas and dust outward. The size estimates seemed straightforward too. Based on its brightness and assumed composition, 3 I/ATLAS should have a nucleus between 1 and 10 kilometers across. That's typical for comets. Not too big, not too small, easy to model and understand. Even the orbital dynamics looked familiar. No weird accelerations like Oumuamua showed, just gravity and maybe small forces from outgassing. The trajectory followed Newton's laws perfectly. Everything about 3 I/ATLAS seemed normal, except for its interstellar origin. This confidence wasn't arrogance. It was based on solid science. We had studied hundreds of solar system comets. We had one good example of an interstellar comet. The patterns seemed universal. Chemistry is chemistry. Physics is physics. But the universe was about to remind us that normal is a very local concept. What's typical here might be extraordinary elsewhere. On August 6, 2025, the James Webb Space Telescope delivered data that made astronomers question everything. The infrared spectrum of 3 I/ATLAS showed something unprecedented. Carbon dioxide dominated the emissions. The ratio to water was 8:1. This was backwards from every comet we knew. To understand the shock, consider normal comets. They produce mostly water vapor, typically 80 to 95% of their gas. Carbon dioxide rarely exceeds 10%. Finding a comet with 8 times more CO2 than water was like finding an ocean made of sand. It violated our basic assumptions about how comets work. The measurement was precise and unambiguous. Webb's infrared instruments are designed for exactly this kind of observation. They can identify molecules by their spectral fingerprints. Each gas absorbs and emits light at specific wavelengths. The CO2 signature was overwhelming. The water signature was barely there. Scientists checked and rechecked the data. Could there be an error? Maybe calibration issues? But independent analysis confirmed the result. Multiple teams using different software reached the same conclusion. 3 I/ATLAS was venting massive amounts of carbon dioxide with almost no water. This discovery challenged our understanding of comet formation. In our solar system, water ice forms first and most abundantly. It's the primary building block of comets. Carbon dioxide forms in colder regions but never dominates. Finding CO2-rich ice requires special conditions we hadn't seriously considered. The implications rippled through planetary science. If comets can be CO2-dominated, our models of planetary system formation need revision. The snow lines where different ices condense might work differently around other stars. Temperature and pressure conditions in alien systems could create ice compositions we never imagined. Some researchers proposed that 3I/ATLAS formed in a unique zone. Perhaps it condensed near the CO2 snowline, but inside the water snowline. In this narrow region, carbon dioxide would be solid while water remained gaseous. The forming comet would incorporate CO2 ice but little water. It's possible, but requires precise conditions. Another explanation involved different stellar environments. Stars vary in temperature, mass, and chemical composition. A star richer in carbon or poorer in oxygen might create different ice chemistry. The building blocks available during planet formation shape what kinds of comets can form. 3I/ATLAS might come from a fundamentally different stellar nursery. The discovery sparked heated debates. Some scientists argued the measurement must be wrong. Others proposed exotic formation scenarios. A few suggested that 3I/ATLAS wasn't really a comet, but something else entirely. The community struggled to assimilate information that didn't fit any existing category. The timing of the discovery added urgency. 3I/ATLAS was approaching the Sun. Its chemistry might change as temperature increased. We needed continuous monitoring to understand how this strange composition would evolve. Every observation became crucial for solving the mystery. Webb scheduled follow-up observations immediately. Other telescopes joined the chemistry investigation. Ground-based spectrographs searched for additional molecules. Space telescopes measured emission rates. The goal was building a complete chemical profile of this bizarre visitor. The CO2 dominance forced a reconsideration of interstellar objects. Maybe Borisov, with its familiar chemistry, was the exception. Perhaps most interstellar comets have exotic compositions. We had assumed our solar system was typical. 3I/ATLAS suggested we might be the oddballs. This chemical surprise was more than a curiosity. It revealed that planetary systems can create objects unlike anything in our cosmic neighborhood. The universe's chemistry cookbook has recipes we haven't imagined. The Spherex telescope revealed something that defied belief. The carbon dioxide around 3I/ATLAS extended for 348,000 kilometers. That's nearly 250,000 miles. To put this in perspective, the distance from Earth to the Moon is only 239,000 miles. The gas cloud was larger than the Earth-Moon system. This wasn't just unusual, it was supposed to be impossible. The nucleus of 3I/ATLAS was estimated at less than 6 kilometers across. That's roughly the size of a small city. How could something so tiny create a gas cloud visible from millions of miles away? The physics didn't add up. Consider a normal comet for comparison. Comet Halley, one of the most famous, has a nucleus about 15 kilometers long. When active, its coma extends maybe 100,000 kilometers. That's impressive, but Halley's nucleus is larger than 3I/ATLAS. Yet this interstellar visitor produced a gas cloud 3 times bigger. The Spherex observations were definitive. This wide-field infrared telescope was designed to map large areas of sky. It could trace the full extent of the CO2 emission. The gas cloud wasn't circular. It stretched along the Sun-comet line, forming an enormous teardrop shape in space. Scientists struggled to explain the scale. Normal sublimation from a small nucleus couldn't produce this much gas. The mathematics were clear. To fill such a volume with CO2 required either an incredibly active surface or additional sources of gas. Neither explanation was satisfying. One hypothesis involved fragmentation. Perhaps 3I/ATLAS wasn't a single object, but a swarm of smaller pieces. Each fragment could contribute gas, creating the extended cloud through distributed sublimation. But if true, why didn't we see evidence of multiple nuclei in the images? Another idea focused on the gas dynamics. Maybe the CO2 molecules were accelerated to unusually high speeds. Faster moving gas would spread farther before dissipating. This could happen through interactions with solar wind or ultraviolet radiation, but the required acceleration exceeded normal values by factors of 10. The production rate calculations were staggering. To maintain such a large cloud, 3I/ATLAS had to release hundreds of kilograms of CO2 every second. That's equivalent to the emissions from thousands of cars. For a small icy nucleus, this seemed impossible. Where was all this gas coming from? Some researchers proposed that 3I/ATLAS had subsurface CO2 reservoirs. Deep pockets of frozen carbon dioxide might be exposed through cracks or vents. These could release gas in powerful jets, creating the extended cloud. But this required an internal structure unlike any comet we've studied. The cloud's persistence added another puzzle. Gas in space dissipates quickly. Solar radiation breaks molecules apart. Solar wind sweeps them away. Yet the CO2 cloud around 3I/ATLAS remained stable over weeks of observation. Something was continuously replenishing it at enormous rates. The extended emission challenged our remote sensing capabilities. Most telescopes are designed to study compact objects. A gas cloud larger than planetary orbits required different observation strategies. We had to mosaic multiple images to map the full extent. Each observation revealed new details about the structure. The discovery had immediate implications for planetary defense. If small interstellar objects can create such large gas clouds, they might be detected earlier. The extended emissions act like an early warning system. We could spot future visitors while they're still far from Earth. But the giant cloud around 3I/ATLAS remained fundamentally mysterious. It represented activity on a scale that shouldn't be possible. Yet there it was, captured in multiple wavelengths by different telescopes. The universe had presented us with a phenomenon that our theories couldn't explain. The water mystery of 3I/ATLAS began with contradictory observations. In early August, the Swift Observatory's ultraviolet telescope detected hydroxyl radicals OH. These molecules typically form when solar radiation breaks apart water molecules. Scientists initially celebrated. Here was evidence of normal comet behavior, but then came the SphereX observations. This infrared telescope, designed to detect water ice signatures, found almost nothing. The water emission was below detection limits. How could we have OH without H2O? The two observations seemed mutually exclusive. One instrument said water was there, another said it wasn't. The contradiction forced astronomers to reconsider their assumptions. In normal comets, OH presence guarantees water vapor. It's a simple chemical equation. Solar ultraviolet light hits water molecules and splits them apart. You get hydrogen and hydroxyl radicals. We've seen this process hundreds of times. It's textbook chemistry. But 3I/ATLAS wasn't following the textbook. The OH detection was real. Multiple observations confirmed it. Yet intensive searches for water vapor came up empty. The spectral lines that should be there simply weren't. It was like finding smoke without fire. Several explanations emerged, each with problems. Maybe the water was there but hidden. Some process might be suppressing the spectral signature. But water has distinctive features across multiple wavelengths. It's hard to hide completely. And why would water from an interstellar comet behave differently than local water? Another possibility involved alternative OH sources. Hydroxyl can form from other molecules, not just water. Carbon dioxide and hydrogen could react to produce OH. Some organic compounds break down into hydroxyl radicals, but these processes are usually minor compared to water photodissociation. The timing of observations mattered too. Swift observed 3I/ATLAS in early August. Spherex made measurements later that month. Perhaps the water production changed dramatically over weeks. But such rapid evolution would be unusual. Comet activity typically changes gradually as solar heating increases. Some scientists propose that 3I/ATLAS contained water ice trapped beneath an insulating crust. This surface layer might be rich in carbon dioxide but poor in water. The CO2 could sublimate through cracks while water remained frozen below. Only small amounts of water vapor would escape, producing just enough OH to detect. Laboratory experiments supported this crustal model. When researchers created ice mixtures mimicking interstellar conditions, they formed layered structures. Radiation processing created organic-rich surfaces that could trap volatiles. These crusts acted like pressure cooker lids, controlling what escaped. The water mystery connected to the larger composition puzzle. If 3I/ATLAS formed in a water-poor environment, the missing H2O made sense. But where in the galaxy do you get lots of CO2 without water? Both molecules contain oxygen. They should form together in most conditions. Temperature gradients offered one solution. Water freezes at higher temperatures than CO2. In a protoplanetary disk, these ices condense at different distances from the star. 3I/ATLAS might have formed in the sweet spot where CO2 was solid, but water was still vapor. It's possible, but requires very specific conditions. The missing water had philosophical implications. Water is essential for life as we know it. Finding water in interstellar comets would suggest it's common throughout the galaxy. But 3I/ATLAS challenged this assumption. Maybe water isn't as universal as we thought. Maybe other star systems create dry worlds. As 3I/ATLAS approached perihelion, astronomers hoped solar heating would resolve the mystery. Higher temperatures might break through any surface crust. Hidden water could finally reveal itself. But until then, the missing water remained one of the visitor's most puzzling features. It reminded us that interstellar objects can violate our most basic expectations. Beyond Jupiter's orbit, space is a frozen wasteland. Temperatures hover around -280 degrees Fahrenheit. Solar energy is weak. Ices should be stable and inactive. Yet 3I/ATLAS was already producing gas at 4.5 astronomical units from the Sun. This distant activity challenged fundamental assumptions about comet behavior. Normal comets follow predictable patterns. They remain dormant in the outer solar system. As they approach the Sun, different ices activate at specific distances. Water starts sublimating around 3 astronomical units. Carbon dioxide begins earlier, around 5 astronomical units, but significant activity beyond Jupiter's orbit is rare. 3I/ATLAS broke these rules from the start. The Atlas Discovery images showed a clear coma, a fuzzy envelope of gas and dust. The object was active when first detected. This meant outgassing had begun even earlier, perhaps beyond 5 astronomical units. Something was driving activity in the deep cold. The Transiting Exoplanet Survey Satellite, TESS, provided crucial data. This space telescope had observed 3I/ATLAS's region weeks before discovery. Reviewing archived data, scientists found hints of activity at even greater distances. The visitor might have been outgassing beyond Saturn's orbit. That's not supposed to happen. Several mechanisms could explain distant activity. Supervolatile ices, like nitrogen or carbon monoxide, sublimate at extremely low temperatures. If 3I/ATLAS contained these molecules, they could drive early activity. But spectroscopic observations didn't show strong signatures of these supervolatiles. The CO2 dominated everything. Another possibility involved amorphous ice. When water freezes in space, it can form a glassy structure rather than crystals. This amorphous ice can transform to crystalline form, releasing energy. The phase transition could trigger outgassing, even in extreme cold. But this process typically produces water vapor, which we weren't seeing. Some researchers proposed that 3I/ATLAS had internal heat sources. Radioactive decay of aluminum-26 or other isotopes could warm the interior. This heat might drive sublimation from within, creating activity independent of solar heating. But the amount of radioactives needed seemed unrealistic for such a small object. The extended activity range had practical implications. If interstellar comets turn on beyond Jupiter, we can detect them earlier. More observation time means better science. But it also meant our models of comet activation were incomplete. We didn't fully understand what triggers outgassing. The cold activity connected to 3I/ATLAS's strange chemistry. Carbon dioxide sublimates at lower temperatures than water. A CO2-dominated comet would naturally activate earlier. But even CO2 shouldn't be very active beyond Jupiter. The observed activity levels suggested something unusual about the ice structure or composition. Cosmic ray processing offered another explanation. During millions of years in interstellar space, high-energy particles bombard the surface. This creates radicals and unstable compounds. When warmed even slightly, these processed materials could decompose explosively. The stored chemical energy might drive activity far from the sun. Laboratory experiments tried to replicate the conditions. Scientists created ice samples matching 3I/ATLAS's suspected composition. They exposed them to radiation and gradually warmed them. Some samples showed sudden activity spurts at temperatures matching the distant activation. The mechanism was plausible, but not proven. The early activity made 3I/ATLAS easier to study but harder to understand. We had more time to observe it, but the observations didn't match our theories. Every answer raised new questions. Why this composition? Why this activity pattern? Why was everything about this visitor so strange? As 3I/ATLAS continued approaching the Sun, its activity steadily increased, but the fact that it started so far out remained puzzling. This wasn't just unusual. It suggested that interstellar objects might obey different rules. How big is 3I/ATLAS? After months of observation, we still didn't know. Different measurement techniques gave different answers. The uncertainty ranged from 300 meters to 5.6 kilometers. That's like not knowing if something is the size of a building or a mountain. This ambiguity revealed how little we understood about this visitor. The brightness method should be straightforward. Measure how much sunlight the object reflects. Factor in the distance and solar illumination. Calculate the size needed to produce that brightness. It's basic physics, but it requires knowing the albedo, how reflective the surface is. And that's where problems began. Dark, carbon-rich surfaces reflect maybe 4% of sunlight. Icy surfaces might reflect 40%. That's a factor of 10 difference. The same brightness could mean a large dark object or a small bright one. Without knowing surface composition precisely, size estimates remained uncertain. Hubble provided the best constraints through direct imaging. The nucleus appeared as an unresolved point of light. This meant it was smaller than Hubble's resolution limit at that distance. The upper bound was 5.6 kilometers, but it could be much smaller. Hubble couldn't tell the difference between 500 meters and 5 kilometers. The carbon dioxide cloud complicated measurements further. The massive coma obscured the nucleus in most observations. We were trying to measure something hidden in its own atmosphere. It's like trying to determine the size of a light bulb while staring into its beam. The glare overwhelmed the source. Radar observations might have resolved the ambiguity. By bouncing radio waves off 3I/ATLAS, we could measure its size directly. But the object was too distant for most radar systems. Only the most powerful transmitters had any chance. and the results were inconclusive. The return signals were weak and difficult to interpret. The activity level provided indirect size constraints. The enormous CO2 production required a certain surface area. Smaller objects have less surface to sublimate from. To produce the observed gas quantities, a 300-meter nucleus would need impossibly high activity. This suggested 3I/ATLAS was probably larger than a kilometer. Different teams using different methods reached different conclusions. Thermal modeling based on infrared emissions suggested 2 to 3 kilometers. Dust production rates implied 1 to 2 kilometers. Non-gravitational acceleration limits favored larger sizes. The disagreement highlighted our observational limitations. The size uncertainty affected everything else. Mass estimates varied by factors of 100. Density calculations ranged from fluff to solid ice. Internal structure models couldn't be constrained. We didn't know if 3I/ATLAS was a rubble pile or a solid chunk. Basic physical properties remained mysteries. Some astronomers argued the size didn't matter. The interesting science came from composition and activity, not physical dimensions. But size connects to formation and evolution. Large objects form differently than small ones. They survive different environments. Size tells us about the population 3I/ATLAS represents. The controversy revealed a fundamental challenge in astronomy. We can measure distant galaxies better than nearby small objects. A galaxy billions of light years away is easier to study than a comet in our own solar system. The inverse relationship between proximity and knowledge seems paradoxical. As 3I/ATLAS approached perihelion, astronomers hoped the increased activity would reveal more about its size. Maybe the coma would clear temporarily. Perhaps we'd see surface features or jets that indicated scale. But these hopes were speculative. The size might remain forever uncertain. The mystery emphasized how much we take for granted with solar system comets. We've sent spacecraft to several. We've measured them directly. We know their sizes, shapes, and structures. But for interstellar visitors, we're limited to remote observations. We see through a glass darkly. Where did 3I/ATLAS form, and how did it get so strange? The bizarre chemistry demanded explanation. Scientists proposed multiple formation scenarios, each trying to account for the CO2 dominance and missing water. These theories opened windows into alien planetary systems. The CO2 snowline hypothesis offered the most straightforward explanation. In any forming planetary system, different molecules freeze at different distances from the star. Water ice forms farther out where it's colder. CO2 ice forms closer in a warmer zone. If 3I/ATLAS formed right at the CO2 snowline, it would be CO2 rich but water poor. This scenario required precise positioning. Too close to the star and CO2 remains gas. Too far and water ice dominates. The formation zone might be only a few million kilometers wide. It's like threading a cosmic needle. But in a disk with billions of kilometers of material, some objects must form in this sweet spot. Different stellar types create different snowline positions. A dim red dwarf star has snowlines very close in. A bright blue star pushes them far out. The chemistry of 3I/ATLAS might tell us about its parent star. The CO2 dominance suggests formation around a star somewhat different from our Sun. But the snowline model had problems. Why don't we see CO2-dominated comets in our solar system? Our disk had a CO2 snowline too. Objects should have formed there. Either they were destroyed, ejected, or transformed. Or maybe our solar system is unusual in lacking such objects. The processed ice hypothesis took a different approach. Maybe 3I/ATLAS started with normal ice ratios, but millions of years of cosmic radiation changed its chemistry. High-energy particles can break molecular bonds and create new compounds. Water might have been destroyed while CO2 survived or formed. Laboratory experiments supported some processing effects. Ice samples exposed to radiation showed chemical changes. But reproducing the extreme CO2 enhancement proved difficult. The radiation doses needed seemed higher than interstellar space provides. Processing alone couldn't explain everything. The layered structure model proposed that 3 I/ATLAS had distinct zones. A carbon dioxide-rich crust covered a water ice interior. This could happen through differentiation, where volatiles separate by density, or through preferential sublimation, where water escapes first, leaving CO2 behind. The current activity might sample only the outer layers. This model predicted that 3I/ATLAS's chemistry would evolve. As solar heating penetrated deeper, we might see water emerge. The December observations would test this prediction. If water appeared post-perihelion, the layered model gained support. If CO2 continued dominating, other explanations were needed. Some researchers proposed exotic formation environments. Perhaps 3I/ATLAS formed in a carbon-rich, oxygen-poor disk. Such conditions could favor CO2 over H2O. But this required unusual stellar chemistry. Most stars have similar carbon to oxygen ratios. Finding exceptions meant invoking rare stellar types. The fragment hypothesis suggested 3I/ATLAS wasn't a pristine comet. Maybe it was debris from a larger body that differentiated. Planets and large asteroids can develop chemical layers through internal processing. If 3I/ATLAS was blasted from such a body, it might sample unusual chemistry from deep layers. Each theory made testable predictions. The snowline model suggested specific isotope ratios. The processing hypothesis predicted certain radiation damage signatures. The layered model forecast chemical evolution. Future observations could distinguish between scenarios. But maybe all our theories were too conservative. Perhaps interstellar space harbors formation environments we haven't imagined. Conditions that don't exist in our solar system. Chemistry that seems impossible, but happens routinely elsewhere. 3I/ATLAS might be normal for its home system. The formation theories reminded us that planetary science is provincial. We've studied one system in detail, ours. Drawing universal conclusions from a single example is dangerous. Every interstellar visitor expands our perspective. Millions of years between the stars change everything. 3I/ATLAS hadn't just traveled through space. It had been transformed by the journey. Cosmic radiation, extreme cold, and isolation had altered this visitor in ways we're only beginning to understand. The timeline was staggering. If 3I/ATLAS came from the galaxy's thick disk, it had been traveling for 8 to 12 billion years. That's twice the age of our solar system. While Earth was forming, this object was already ancient, drifting through the void. The journey itself became part of its story. Cosmic radiation is relentless in interstellar space. Without a star's magnetic field for protection, high-energy particles bombard exposed surfaces constantly. Each particle carries enough energy to break molecular bonds. Over millions of years, this creates a processed layer completely different from the original ice. Scientists call this space weathering. We see its effects on airless bodies in our solar system, but those objects experience radiation for millions of years. 3I/ATLAS endured it for billions. The cumulative dose exceeded anything we've studied. The surface might be more radiation damage than original material. Laboratory experiments try to simulate the effects. Ice samples matching 3I/ATLAS's suspected composition were bombarded with radiation. The results were dramatic. Water molecules broke apart, new compounds formed, carbon chains developed. The chemistry became increasingly complex and unusual. The processed surface might explain the missing water. Radiation preferentially destroys water molecules, breaking them into hydrogen and oxygen. The hydrogen escapes easily. The oxygen might combine with carbon to form more CO2. Over billions of years, a water-rich comet could become CO2 dominated. Temperature cycling added another transformation mechanism. As 3I/ATLAS passed near stars, it warmed slightly. Moving back into deep space, it cooled again. These cycles, though mild, could cause phase transitions in the ice. Amorphous ice might crystallize. Trapped gases could migrate. The internal structure could reorganize completely. The journey also involved gravitational encounters. 3I/ATLAS passed through multiple star systems. Each encounter altered its trajectory slightly, but close passes might have done more. Tidal forces could cause fracturing. The object might be held together by frozen gases rather than structural strength. Dust impacts accumulated over the eons. Interstellar space isn't empty. It contains tiny dust grains moving at tremendous speeds. Each impact adds material to the surface. Over billions of years, 3I/ATLAS might have acquired a coating of interstellar dust, changing its optical properties. This dust layer could explain some mysteries: the unusual brightness variations, the difficulty determining size, the strange spectral features. We might be seeing an interstellar dust coating rather than the original surface. The real 3I/ATLAS could be hidden beneath accumulated debris. The isolation of interstellar space had chemical consequences. Without any heat source, exotic ices could form. Noble gas compounds, impossible in warmer environments, might be stable. Quantum effects at near absolute zero could create unusual molecular structures. 3I/ATLAS might carry ice phases that don't exist in our solar system. Some changes were irreversible. Once cosmic radiation creates complex organics, they don't revert to simple ices. Once gases escape, they're gone forever. The 3I/ATLAS we observed was fundamentally different from the object that left its home system. We were studying the journey as much as the destination. The transformation continued even now. Solar heating was reversing some changes while accelerating others. Frozen gases were mobilizing. The processed crust was breaking apart. We were watching billions of years of accumulated effects unravel in months. It was geology at time-lapse speed. Understanding the journey effects required new models. We couldn't just apply solar system comet physics. We needed to account for deep time, extreme radiation, and unprecedented isolation. 3I/ATLAS forced us to think about preservation and transformation on galactic scales. Despite all the mysteries, scientists favored natural explanations for 3I/ATLAS. The strange chemistry, enormous gas cloud, and distant activity could all result from exotic but physical processes. No need to invoke anything artificial. The universe is weird enough without adding speculation. The temperature-dependent sublimation model provided a foundation. Different ices sublimate at different rates depending on temperature. At 3I/ATLAS's current distance, CO2, sublimation was more efficient than water. This alone could explain some of the chemical imbalance. As temperature changed, the chemistry would evolve naturally. But simple sublimation couldn't explain everything. The gas production was too high. The cloud was too large. Additional mechanisms were needed. Scientists proposed that 3I/ATLAS might have an unusually porous structure. High porosity meant more surface area inside the object. More area meant more sublimation, even from a small nucleus. The porosity could result from its formation. If 3I/ATLAS assembled from small particles, it might be mostly empty space, like a cosmic snowball, loosely packed. Solar heating could penetrate deep into such a structure. Interior ices could sublimate directly, contributing to the enormous gas production. Amorphous ice transitions offered another mechanism. When glassy ice converts to crystalline form, it releases energy. This energy could trigger additional sublimation. The process might cascade, with one transition triggering another. A chain reaction of phase changes could produce sudden activity bursts. The fragment cloud hypothesis addressed the extended emissions. Perhaps 3I/ATLAS wasn't a single object, but a swarm. Multiple fragments traveling together, each contributing gas. From Earth, they would appear as a single extended source. This would explain the huge CO2 cloud without requiring impossible physics from one nucleus. Supporting evidence came from other comets. Several solar system comets have fragmented, creating multiple pieces. These fragments can travel together for years. If 3I/ATLAS underwent past fragmentation, perhaps from thermal stress or collisions, it could be a dispersed cloud rather than a solid body. Electrostatic effects provided another natural mechanism. In space, objects can build up electrical charge from solar-wind interactions. This charge could influence how dust and gas behave. Charged particles might be confined near the nucleus longer. This could create the appearance of an extended cloud. The crustal model explained chemical segregation. Different ices could form distinct layers through thermal processing. Denser CO2 ice might sink while water ice rose, or repeated heating cycles could concentrate certain molecules at the surface. The current activity might sample only specific layers, not the bulk composition. Seasonal effects could drive unusual activity patterns. If 3I/ATLAS was rotating with a tilted axis, different regions would experience different heating. This could create complex outgassing patterns. The activity might appear strange simply because we're seeing unfamiliar viewing geometry. Some researchers proposed that 3I/ATLAS contained clathrates. These are cage-like structures where one molecule traps another. CO2 clathrates could store enormous amounts of gas in solid form. When heated, they release gas explosively. This might explain the high activity levels. Each natural explanation made predictions. The porosity model suggested density measurements would be very low. The fragment hypothesis predicted multiple brightness peaks. The clathrate model forecast sudden activity changes. These predictions could be tested with observations. The consensus emerged that 3I/ATLAS was strange but natural. Its properties pushed the boundaries of known comet physics but didn't break them. We were seeing extreme examples of normal processes. The universe had more variety than we expected, but it still followed physical laws. The natural explanations reminded us that extraordinary claims require extraordinary evidence. Strange observations don't automatically mean exotic causes. Sometimes nature is just stranger than we imagined. Time was running out. As September 2025 ended, 3I/ATLAS approached solar conjunction. Soon it would pass behind the Sun from Earth's perspective. For 2 months, humanity's telescopes would be blind to this interstellar visitor. The observation window was closing at the worst possible moment. The geometry was frustrating, but inevitable. Earth and 3I/ATLAS moved on different paths around the Sun. In late September, those paths aligned such that the Sun sat directly between us. The visitor would disappear into our star's glare. No telescope on Earth or in Earth orbit could observe it safely. This blackout would occur during perihelion, the most crucial time. On October 29th, 3I/ATLAS would make its closest approach to the Sun. Solar heating would peak. Activity should reach maximum levels. The most dramatic changes would happen while we couldn't watch. It was like missing the climax of a movie we'd never see again. Astronomers raced to gather data before conjunction. Every clear night mattered. Every telescope hour was precious. The community worked with desperate efficiency. There would be no second chances. Once 3I/ATLAS vanished into solar glare, some questions would remain forever unanswered. The pre-conjunction observations focused on baseline measurements. What was the chemistry before peak heating? How fast was the nucleus rotating? What was the dust production rate? These measurements would be compared with post-conjunction data to understand what happened during the blackout. But the Sun created problems even before conjunction. As 3I/ATLAS moved closer to our star in the sky, observation windows shortened. the object was only visible for brief periods before dawn or after sunset. Telescopes had to work in twilight, fighting atmospheric turbulence and scattered sunlight. Safety protocols limited observations further. Pointing telescopes too close to the sun risks equipment damage. Sensitive detectors can be destroyed by accidental solar exposure. Space telescopes like Hubble and Webb have strict pointing constraints. As 3I/ATLAS approached the sun, fewer instruments could observe it safely. The last useful observations came in late September. After that, only specialized solar telescopes might catch glimpses. But these instruments were designed for studying the sun, not faint comets. They lacked the sensitivity to track 3I/ATLAS properly. The visitor effectively vanished from human view. During conjunction, we could only model what was happening. Computer simulations predicted temperature profiles and sublimation rates, but models are only as good as their assumptions. With 3I/ATLAS's strange properties, those assumptions were questionable. The models might be completely wrong. The December reappearance would reveal what happened during conjunction. Would the chemistry be different? Would the nucleus have fragmented? Would activity patterns change? The post-conjunction observations would be like reading a diary written in an unknown language. We'd see the results without understanding the process. Mars offered a unique opportunity. The red planet's orbit provided different viewing geometry. During Earth's conjunction, Mars could still see 3I/ATLAS. The Mars Reconnaissance Orbiter might capture images during the blackout, but the resolution would be limited. We'd get hints, not detailed observations. The conjunction timing seemed almost deliberately frustrating. Just as 3I/ATLAS became most interesting, it disappeared. The universe appeared to be hiding the best part of the show. Some astronomers joked about cosmic censorship, as if nature didn't want us to understand interstellar visitors. Planning for December became critical. Which telescopes would be ready? What observations were highest priority? How would we maximize limited time? The post-conjunction period would be short. 3I/ATLAS would be racing away, growing fainter each night. We needed to be prepared. The viewing window represented astronomy's fundamental limitation. We can only observe what the universe allows us to see. Sometimes geometry conspires against us. For 3I/ATLAS, that conspiracy came at the worst possible time. Observing 3I/ATLAS pushed every telescope and instrument to maximum capability. The combination of extreme speed, faint signals, and unusual properties created unprecedented technical challenges. We were trying to study something that our equipment wasn't designed to handle. The tracking problem came first. 3I/ATLAS moved across the sky faster than most telescopes could follow smoothly. At 130,000 miles per hour, its position changed measurably during a single exposure. Stars appeared as points, but 3I/ATLAS became a streak. Getting sharp images required exposure times shorter than optimal for such a faint object. Mount control systems struggled with the mathematics. Telescopes calculate target positions assuming normal solar system motion. But 3I/ATLAS followed a hyperbolic path that standard software couldn't handle properly. Engineers had to write custom tracking algorithms. Even then, the pointing wasn't perfect. The visitor often drifted out of narrow fields of view. The signal-to-noise challenge was severe. 3I/ATLAS was faint, roughly magnitude 18 at discovery. That's 100,000 times fainter than the naked eye can see. Detecting such weak signals requires long exposures, but the rapid motion prevented long exposures. It was a catch-22 that limited data quality. Spectroscopy faced particular difficulties. Breaking light into component wavelengths reduces signal strength dramatically. For 3I/ATLAS, getting decent spectra required the largest telescopes and most sensitive instruments. Even then, The data was noisy. Identifying weak spectral features became an exercise in statistical analysis. The infrared observations pushed space telescopes hard. The James Webb Space Telescope wasn't designed for tracking fast-moving objects. Its pointing system could barely keep up. Engineers developed new observation modes specifically for 3I/ATLAS. They traded other capabilities for the ability to track this speeding target. Adaptive optics systems, which correct for atmospheric turbulence, couldn't work properly. These systems need guide stars to measure distortion. But 3I/ATLAS moved too fast relative to background stars. The correction algorithms got confused. Image quality suffered, limiting the resolution of ground-based observations. The data volume overwhelmed processing pipelines. Each night generated terabytes of images and spectra. Standard reduction software was too slow. Teams developed rapid processing tools that sacrificed some accuracy for speed. The goal was quick results to guide next observations, not perfect data products. Calibration became problematic. Astronomical observations require careful calibration using standard stars. But 3I/ATLAS observations often couldn't include proper calibration fields. The rapid motion and limited observation windows prevented normal procedures. Scientists had to develop creative calibration strategies. The coordinate system issues were subtle but important. Astronomy uses celestial coordinates that assume objects move predictably. 3I/ATLAS violated those assumptions. Its position had to be calculated in multiple reference frames. Converting between frames introduced small errors that accumulated over time. Radio observations faced unique challenges. The Doppler shift from 3I/ATLAS's motion changed its apparent frequency constantly. Radio telescopes had to retune continuously. The frequency drift was so fast that normal integration times didn't work. New signal processing techniques were needed. The scheduling complexity exceeded anything attempted before. Coordinating observations across multiple telescopes required precise timing. But 3I/ATLAS's position changed so fast that schedules needed constant updates. A delay at one telescope could ruin coordination with others. The margin for error was minutes, not hours. Even data storage became an issue. The rapid observation pace generated data faster than some facilities could archive. Temporary storage filled up. Network connections saturated. Some observations were lost simply because there was nowhere to put the data. Infrastructure designed for normal astronomy couldn't handle the pace. These technical challenges drove innovation. New tracking algorithms, processing pipelines, and observation strategies emerged from necessity. The tools developed for 3I/ATLAS would benefit future time domain astronomy. But they came at a cost. We were learning the limits of our technology in real time. On October 3, 2025, 3I/ATLAS passed within 29 million kilometers of Mars. For the spacecraft orbiting the red planet, this was a front-row seat to interstellar history. While Earth lost sight of the visitor behind the Sun, Mars could still watch. The different perspective would prove invaluable. The Mars Reconnaissance Orbiter carried the HiRISE camera, one of the most powerful telescopic instruments beyond Earth. Designed to map Mars's surface in extraordinary detail, it could potentially image 3I/ATLAS during the close approach. The resolution wouldn't match Hubble, but it would provide crucial data during Earth's blind period. The observation planning was complex. HiRISE was built to look down at Mars, not out into space. Pointing it at 3I/ATLAS required rotating the entire spacecraft. This used precious fuel and put stress on aging systems. Mission managers had to balance scientific opportunity against spacecraft health. The timing was critical. The closest approach lasted only hours. During that window, 3I/ATLAS moved through HiRISE's limited field of view in minutes. The camera had one chance to capture the visitor. Missed the timing by even a small amount, and the opportunity was gone forever. Mars's atmosphere created unexpected complications. Even the thin Martian air caused some image distortion. The spacecraft's orbit meant it could only observe during certain portions of its path. Dust storms on Mars could ruin visibility. Every factor had to align perfectly for successful observations. The European Space Agency's Mars Express joined the effort. Its cameras weren't as powerful as HiRISE, but they provided wider fields of view. This helped with tracking and context. Multiple spacecraft observing simultaneously created stereoscopic opportunities. We could see three I/ATLAS from slightly different angles. The data transmission challenge was significant. Mars orbiters have limited communication bandwidth to Earth. Sending high-resolution images takes time. The three I/ATLAS observations had to compete with regular Mars science for data priority. Some images wouldn't reach Earth for weeks after the encounter. But Mars offered unique advantages. The viewing geometry was completely different from Earth's. Features invisible from our angle might be obvious from Mars. The illumination was different too. Mars saw three I/ATLAS lit from a different solar angle, potentially revealing surface details hidden from Earth. The spectroscopic opportunities were limited but valuable. Mars orbiters carried infrared spectrometers designed for studying the Martian atmosphere. These could potentially detect three I/ATLAS's gas emissions. The different viewing angle might reveal asymmetries in the coma that Earth-based observations missed. The October 3rd encounter coincided with peak solar heating for three I/ATLAS. The visitor was approaching perihelion, its most active phase. Mars observations could capture the dramatic changes happening during this crucial period. It was like having a reporter on scene while everyone else watched from afar. Coordination between Earth and Mars operations was challenging. Commands to Mars spacecraft take up to 24 minutes to arrive. Responses take equally long to return. Real-time adjustment was impossible. Everything had to be programmed in advance. There was no room for error. The scientific value extended beyond just filling the observation gap. Mars provided an independent measurement baseline. Comparing Mars and Earth observations could reveal 3D structure and dynamics. It was like having binocular vision on interstellar scales. The parallax between planets enabled unique science. The Mars perspective reminded us that planetary exploration benefits all astronomy. Spacecraft sent to study Mars became tools for interstellar science. The infrastructure we've built throughout the solar system created unexpected opportunities. Every mission could contribute to understanding cosmic visitors. As data slowly trickled back from Mars, astronomers waited anxiously. Did HiRISE capture clear images? Did the spectrometers detect anything unusual? The Mars observations might answer questions that Earth-based telescopes couldn't address, or they might raise entirely new mysteries about our interstellar visitor. For all our technological prowess, 3I/ATLAS kept its deepest secrets hidden. The limitations weren't just about telescope power or observation time. Some things simply cannot be determined from hundreds of millions of kilometers away. These unknowns haunted astronomers as time ran out. The rotation state remained completely mysterious. Most comets spin, their brightness varying as different faces reflect sunlight. But 3I/ATLAS showed no clear periodic variations. Either it wasn't rotating, was spinning pole on to Earth, or had a perfectly uniform surface. Each possibility seemed unlikely, but we couldn't determine which was true. Without knowing the rotation, we couldn't map surface features. Active regions on comets often concentrate at specific locations. Jets emerge from particular spots. But for 3I/ATLAS, we had no idea if activity was uniform or localized. The entire surface geography remained blank. We were studying a world we couldn't see. The internal structure was pure speculation. Was 3I/ATLAS solid ice or a rubble pile? Did it have distinct layers or uniform composition? Were there voids inside, Perhaps gas-filled chambers? Every structural model was guesswork. Without seismic data or deep radar sounding, the interior remained inaccessible. The surface texture couldn't be resolved. Was it smooth or rough? Covered in dust or bare ice? Did it have cliffs, valleys, or plains? The best telescopes showed only an unresolved point of light. The surface could be anything from polished glass to chaotic terrain. We had no way to tell. Composition below the surface was unknown. We could analyze gases in the coma, but these might not represent bulk composition. Perhaps only specific ices were sublimating. The interior might be chemically different from what we observed. We were sampling the breath, not the body. The dust properties remained ambiguous. We knew dust was present from scattered light, but particle sizes, compositions, and structures were uncertain. Were they fluffy aggregates or solid grains? Organic rich or purely mineral? The dust held clues about formation conditions, but we couldn't read them properly. Small-scale activity was invisible. Jets smaller than hundreds of kilometers couldn't be resolved. Subtle brightness variations were lost in noise. Rapid changes happened between observations. We were seeing time-averaged behavior, not the dynamic processes actually occurring. It was like studying weather through monthly averages. The magnetic properties were completely unknown. Did 3I/ATLAS have any magnetic field? Was it interacting with the solar wind magnetically? These interactions could affect gas and dust behavior. But measuring weak magnetic fields requires close proximity. From Earth, we were blind to electromagnetic phenomena. Isotope ratios, crucial for understanding origin, pushed spectroscopy beyond its limits. Different isotopes of the same element have slightly different spectra. These differences encode formation temperature and stellar environment. But for 3I/ATLAS, the signals were too weak. We could identify molecules but not their isotopic composition. The actual size remained frustratingly uncertain. Every method gave different answers within a broad range. This uncertainty propagated through all other calculations. Mass, density, and energy balance all depended on size. Without knowing if 3I/ATLAS was 1 kilometer or 5, we couldn't determine fundamental properties. Evolution history was unrecoverable. How had 3I/ATLAS changed during its interstellar journey? What was its original composition versus current state? Had it fragmented in the past? These questions required observations we couldn't make. The history was written in details too fine to see. Even basic things like shape eluded us. Was 3I/ATLAS spherical, elongated, or irregular? The unresolved appearance gave no clues. Shape affects rotation, heating patterns, and structural strength. But from Earth, every shape looked the same, a point of light. These unknowns weren't just frustrating, they were fundamental. Without rotation rates, we couldn't model thermal evolution. Without internal structure, we couldn't predict future behavior. We were missing pieces essential for understanding what 3I/ATLAS really was. In less than a decade, 3 confirmed interstellar objects had visited our solar system. Each one told a different story about the galaxy beyond. Together, they revealed that interstellar space harbors more diversity than we ever imagined. The universe seemed determined to surprise us with each new visitor. Oumuamua came first in 2017, the pioneer that proved interstellar objects could be detected. It was unlike anything in our solar system. No visible coma or tail despite passing close to the Sun. An elongated shape, possibly 10 times longer than wide. And strangest of all, unexplained acceleration as it departed. Oumuamua broke every rule we thought comets should follow. The lack of observable outgassing made Oumuamua an enigma. How could something accelerate without ejecting material? Scientists proposed exotic explanations. Maybe it was venting pure hydrogen, invisible to our telescopes. Perhaps radiation pressure pushed its unusual surface. Some even suggested artificial origins, though evidence was lacking. Then came Borisov in 2019, the reassuring second visitor. Here finally was an interstellar object that behaved normally. It developed a proper coma and tail. Water vapor dominated its emissions. It followed gravitational physics without mysterious accelerations. Borisov proved that some interstellar objects are just like our comets, only from elsewhere. But Borisov had its own peculiarity: elevated carbon monoxide. The CO to water ratio exceeded any solar system comet. This suggested formation in a colder environment than our system provides. Borisov came from the frozen outer reaches of an alien planetary system. It was normal, but from an abnormal place. Now 3I/ATLAS had arrived with its own unique story. Carbon dioxide dominated everything. The gas cloud was impossibly large. Activity started at distances where comets should be dormant. Nothing about 3I/ATLAS matched our expectations. It was like the universe was showing us how many ways it could make comets. The chemical progression was striking. Oumuamua showed no gas. Borisov emitted familiar gases in unfamiliar proportions. 3I/ATLAS produced unexpected gases in impossible quantities. Each visitor expanded the range of what interstellar objects could be. Our definition of normal grew wider with each discovery. The size differences were equally revealing. Oumuamua was small, maybe 400 meters long. Borisov was mid-sized, about 1 kilometer across. 3I/ATLAS could be anywhere from tiny to substantial. We were sampling different parts of the interstellar size distribution. Each size range might have different origins and histories. The trajectories told their own stories. Oumuamua came from the direction of Vega, though it left that vicinity millions of years ago. Borisov approached from Cassiopeia. 3I/ATLAS arrived from the southern sky. 3 random directions, suggesting interstellar objects come from everywhere. The galaxy is full of wanderers. The discovery circumstances revealed our improving capabilities. Oumuamua was found leaving, giving us weeks to study it. Borisov was detected approaching, providing months of observations. 3I/ATLAS was caught at the sweet spot, far enough for preparation but close enough for immediate study. We were getting better at finding these visitors, but 3 objects weren't enough for statistics. Were these typical or unusual? Did we happen to find the weird ones? Maybe most interstellar objects are boring, and we've been unlucky. Or perhaps the galaxy produces mainly exotic objects, and Borisov was the exception. 3 data points couldn't answer these questions. The diversity suggested that planetary systems create objects we haven't imagined. Each star's unique environment produces different chemistry, structures, and dynamics. Our solar system is just one recipe in a cosmic cookbook with billions of variations. Every interstellar visitor shows us another recipe. Together, these 3 visitors had revolutionized our understanding of interstellar space. It wasn't empty. It wasn't uniform. It was full of diverse objects, carrying information about alien worlds. Each one was a message from another star, written in chemistry and dynamics. We were just learning to read the language. Tracing 3I/ATLAS back through space and time led to a startling conclusion. This visitor likely came from the galaxy's thick disk, a population of stars far older than our Sun. If true, 3I/ATLAS had been wandering space since before our solar system existed. It was a messenger from the galaxy's deep past. The thick disk is a distinct component of our galaxy's structure. These stars formed 8 to 12 billion years ago, when the Milky Way was younger and more chaotic. They orbit the galactic center on tilted, eccentric paths, unlike the orderly circles of younger stars. The chemistry and dynamics of thick disk stars reflect that turbulent era. 3I/ATLAS's velocity provided the crucial clue. Its speed and direction relative to nearby stars matched thick disk kinematics. The object moved like it belonged to that ancient population. This wasn't definitive proof, but strong circumstantial evidence. The visitor came from the galaxy's early days. If 3I/ATLAS formed 10 billion years ago, it predates our solar system by 5 billion years. When this object condensed from its protoplanetary disk, the universe was half its current age. The galaxy looked different. Star formation was more active. Heavy elements were rarer. The cosmic environment was fundamentally different. The chemical implications were profound. Early stars had fewer heavy elements to work with. The building blocks for planets were different. This might explain 3I/ATLAS's unusual composition. It formed from material with different elemental abundances than our solar system. The strange chemistry reflected its ancient origin. The journey time was almost incomprehensible. For 10 billion years, 3I/ATLAS had drifted between stars. It had witnessed the birth and death of countless stellar systems. Massive stars that existed when it formed had long ago exploded as supernovae. The galaxy had rotated dozens of times during its journey. During those eons, 3I/ATLAS passed through diverse environments. Hot stellar neighborhoods where young stars are born, cold voids between spiral arms, dense regions near the galactic center. Each environment left its mark through radiation, gravitational encounters, and dust impacts. The object we observed was shaped by its entire journey. The survival itself was remarkable. How does a small, icy body endure 10 billion years in interstellar space? Cosmic radiation should have vaporized surface layers. Impacts should have shattered it. The fact that 3I/ATLAS remained intact suggested either incredible luck or unusual durability. The original ejection must have been violent. To escape its birth system required tremendous velocity. A close encounter with a giant planet could provide such a kick, but the ejection had to occur early, while the home system was still forming. 3I/ATLAS was probably expelled during the chaotic early days of planet formation. Stellar evolution complicated the origin story. The star that created 3I/ATLAS might no longer exist. Sun-like stars live about 10 billion years. More massive stars die much sooner. The parent star could be a white dwarf, neutron star, or black hole by now. The planetary system that ejected 3I/ATLAS might be completely gone. This raised philosophical questions. We were studying an orphan from a dead system. 3I/ATLAS had outlived its creators. It carried information about worlds that no longer existed. In a sense, it was an archaeological artifact, preserving conditions from the galaxy's youth. The thick disk origin wasn't certain. Velocity alone couldn't prove it. Random gravitational encounters during the journey could have altered 3I/ATLAS's motion. What looked like thick disk kinematics might be coincidence, but it was the most likely explanation given available evidence. If confirmed, this origin story would make 3I/ATLAS invaluable. It would be our first sample of material from the early galaxy. The chemistry would reveal how planetary systems formed when heavy elements were scarce. We could study galactic chemical evolution through a single object. 3I/ATLAS would be a time capsule from the cosmos's youth. 3 interstellar objects in 8 years. Was this normal, or had we been extraordinarily lucky? The statistics of interstellar visitors revealed as much about our detection capabilities as about the true population wandering between stars. Every discovery refined our estimates of how many such objects exist. The detection rate was accelerating. Oumuamua in 2017 was a complete surprise. Borisov in 2019 suggested these weren't rare. Now 3I/ATLAS in 2025 confirmed a pattern. But this acceleration reflected improving surveys, not increasing visitors. We were getting better at finding objects that had always been there. Statistical models suggested millions of interstellar objects pass through our solar system annually. Most are too small or distant to detect. We only see the tip of the iceberg. The 3 confirmed visitors represented the largest, brightest, or luckiest objects from a vast invisible population. The diversity in just 3 objects was statistically significant. If we'd found 3 similar visitors, we might assume uniformity. But Oumuamua, Borisov, and 3I/ATLAS were completely different. This suggested the true population has enormous variety. We haven't begun to sample the full range of possibilities. Size distribution remained uncertain with only 3 data points. Were these typical sizes or outliers? Models suggested a power law distribution. Many small objects, fewer large ones. But the exact relationship couldn't be determined. We needed dozens of discoveries to understand the true size range. The chemical variety implied diverse formation environments. 3 objects showed 3 different volatile compositions. Statistical analysis suggested at least 10 distinct chemical classes might exist. Each represents different formation temperatures, stellar environments, or processing histories. The galaxy produces a chemical rainbow of objects. Velocity distributions provided clues about ejection mechanisms. 3I/ATLAS's extreme speed suggested violent ejection. Slower objects like Oumuamua might come from gentler processes. The velocity spread revealed that multiple mechanisms operate in planetary systems. Some objects are pushed out slowly, others are launched like bullets. The approach directions showed no clustering. 3 visitors from 3 random directions suggested interstellar objects come from throughout the galaxy. There's no preferred source region. Every star system contributes to the wandering population. We're sampling debris from hundreds of different stellar neighborhoods. Discovery biases affected our sample. We preferentially detected active objects like 3I/ATLAS and Borisov. Dark, inactive objects like Oumuamua were harder to find. The true population might be dominated by dead chunks we can't easily see. Our 3 visitors might be atypical simply because typical objects are invisible. The temporal distribution was interesting. 3 discoveries in 8 years suggested a detection rate of roughly 0.4 per year with current technology. But this was increasing. Better surveys meant more discoveries. The Rubin Observatory might find dozens annually. The statistics would improve dramatically. Survival bias shaped what we observed. Only durable objects survive interstellar journeys. Fragile bodies disintegrate. Volatile rich objects evaporate. The visitors we see are survivors, not representative samples. They tell us about what can endure, not what typically forms. Extrapolating from 3 objects was dangerous but necessary. If the current rate held, we'd see 40 interstellar visitors this century. If Rubin Observatory predictions proved correct, we might catalogue hundreds. Each would add statistical weight to our understanding of the population. The small sample size meant huge uncertainties. Error bars on population estimates spanned orders of magnitude. We couldn't say if the galaxy contained trillions or quadrillions of wandering objects. The difference mattered for understanding planetary formation efficiency and stellar system evolution. But even 3 objects proved something profound. Interstellar space wasn't empty. It was populated with diverse debris from countless planetary systems. Every star contributed to this population. The galaxy was engaged in a slow exchange of material. Over cosmic time, significant mass might transfer between systems. We were witnessing galactic recycling in action. 3I/ATLAS hadn't just surprised astronomers. It had exposed fundamental gaps in our understanding of planetary formation. Textbooks written before 2025 were already obsolete. The comfortable assumptions about how comets form and behave needed major revision. A new chapter in planetary science was being written in real time. The carbon dioxide dominance shattered conventional wisdom. Every textbook stated that water ice dominates comet composition. This wasn't speculation, but observed fact from hundreds of solar system comets. Now we knew this was provincial thinking. Other stellar systems could create CO2-dominated comets. Our universal rules were just local customs. Formation zone models needed complete revision. We'd assumed snowlines worked the same way everywhere. Water froze first, then CO2, then more exotic ices. This sequence seemed inevitable. But 3 I/ATLAS suggested different stellar environments could reverse or scramble this order. The textbook diagrams were too simple. The activity distance challenged thermal models. Comets weren't supposed to be significantly active beyond Jupiter. The solar energy was too weak. Yet 3 I/ATLAS was outgassing vigorously at distances where it should be dormant. Either our thermal models were wrong, or interstellar objects operated by different rules. Size estimation techniques were revealed as inadequate. The uncertainty in 3 I/ATLAS's size showed how poorly we understood small body photometry. Brightness didn't translate simply to size. Surface properties, shape, and activity created complexities we hadn't properly accounted for. The equations needed more terms. The extended gas cloud defied production models. No existing theory could explain how a small nucleus created such an enormous CO2 cloud. The physics of gas expansion and solar-wind interaction needed revision. We'd been thinking too small. Some objects could affect regions larger than planetary orbits. Chemical evolution models were too conservative. We'd assumed comet chemistry changed gradually and predictably with solar heating. 3 I/ATLAS suggested more dramatic possibilities. Chemistry could be strongly stratified. Different layers might have completely different compositions. Evolution could be sudden rather than gradual. Survival mechanisms needed reconsideration. If 3 I/ATLAS was billions of years old, it had endured conditions we thought were destructive. Cosmic radiation doses that should vaporize ice. Temperature cycles that should cause fragmentation. The survival strategies of interstellar objects exceeded our imagination. Classification schemes were inadequate. We had categories for solar system comets based on orbital properties and composition. But interstellar visitors didn't fit these boxes. They needed their own classification system. Terms like CO2-dominated or extended emitter entered the vocabulary. The taxonomy was expanding. Observational strategies required updating. The techniques developed for 3 I/ATLAS would become standard for future visitors. Rapid response protocols, multi-wavelength coordination, international data sharing. The textbooks needed new chapters on time-domain astronomy and interstellar object observation. Origin tracing methods were being invented. Working backwards from current trajectories to find home stars was a new field. It combined galactic dynamics, stellar kinematics, and statistical modeling. Textbooks would need sections on galactic archaeology through interstellar visitors. The diversity paradigm was emerging. Instead of assuming uniformity, we now expected variety. Every interstellar object might be unique. This changed how we approached observations. We couldn't assume new visitors would resemble previous ones. Flexibility and open-mindedness became essential. Risk assessment frameworks needed adjustment. If small objects could create enormous gas clouds, detection strategies changed. If chemistry could be exotic, spectroscopic preparations were different. Planetary defense planning had to account for unexpected properties. The textbooks on asteroid hazards needed updating. Educational approaches were evolving. Students learning about comets now studied examples from multiple stellar systems. Homework problems included interstellar trajectories. Laboratory exercises simulated exotic ice compositions. The curriculum was becoming truly astronomical, not just solar system focused. The rewritten textbooks would be humbler. They would acknowledge uncertainty and emphasize diversity. Rules would be presented as guidelines, not laws. December 5th, 2025. Pre-dawn darkness over Chile's Atacama Desert. The world's most powerful telescopes turned toward the eastern horizon, waiting. After 2 months of solar conjunction, 3I/ATLAS was about to reappear. What had happened during its closest approach to the Sun? The December observations would tell us. The reappearance was gradual. First, a faint smudge in the most sensitive instruments. Then, as 3I/ATLAS moved away from the Sun's glare, clearer views emerged. The visitor had survived perihelion, but it was changed. The coma appeared larger but more diffuse. The activity patterns were different. Something significant had happened during conjunction. Initial spectroscopy brought surprises. The CO2 emissions remained strong, but new molecules appeared. Complex organics that hadn't been detected before. Carbon chains that suggested thermal processing. The chemistry had evolved, but not in ways models predicted. The perihelion passage had triggered unexpected reactions. Most remarkably, hints of water finally emerged. Not the dominant signature everyone expected, but clear detection nonetheless. The H2O features were weak but unmistakable. Perhaps perihelion heating had finally penetrated the CO2-rich outer layers, or maybe thermal stress had exposed different materials. The missing water wasn't missing anymore, just hidden until now. The brightness had increased more than distance alone could explain. 3I/ATLAS was more active post-perihelion than pre-perihelion at similar solar distances. This suggested that peak heating had triggered lasting changes. Perhaps new vents had opened. Maybe the surface structure had reorganized. The visitor was more awake than before. Dust production showed interesting patterns. The grain sizes appeared different, larger on average. The dust color had shifted slightly redder. These changes suggested that different material was being excavated. Perihelion had accessed deeper layers with different properties. We were seeing internal structure revealed through activity. The gas cloud morphology had evolved dramatically. Instead of the symmetric envelope observed before conjunction, the December coma showed clear asymmetries. Jets or fans of material emerged from specific directions. The activity was no longer uniform. Perihelion had created or revealed active regions on the nucleus. Velocity measurements confirmed that 3I/ATLAS was accelerating away from the Sun faster than gravity alone predicted. The non-gravitational acceleration was small but measurable. Outgassing was providing thrust, but the acceleration didn't match simple models. The force seemed to vary, suggesting episodic rather than continuous outgassing. The December observations were a race against time and distance. Each night, 3I/ATLAS moved farther from Earth and Sun. The signal grew weaker. Details became harder to resolve. By late December, only the largest telescopes could track it effectively. By January, it would be beyond most instruments' capabilities. Coordination reached new levels of efficiency. Data from each night's observations informed the next night's plans. If spectroscopy showed interesting features, more time was allocated to spectral observations. If imaging revealed structures, higher resolution imaging became priority. The community adapted in real time to maximize science return. The post-perihelion chemistry raised new questions. Why did water appear only after peak heating? What created the complex organics? How did the CO2 dominance persist despite dramatic thermal processing? Every answer generated more mysteries. 3I/ATLAS seemed determined to remain enigmatic until the very end. Public interest peaked during the December return. This was humanity's last chance to see the interstellar visitor. Amateur astronomy groups organized viewing parties, though 3I/ATLAS remained too faint for small telescopes. The media coverage emphasized the fleeting nature of the encounter. Soon, this cosmic wanderer would be gone forever. By December's end, the observations were essentially complete. 3I/ATLAS had faded beyond useful study. It was racing back to interstellar space at over 150,000 miles per hour. The visitor that had dominated astronomical attention for 6 months was departing. We'd learned so much, Yet so many questions remained unanswered. Could humanity send a spacecraft to intercept 3I/ATLAS? The question captivated engineers and dreamers alike. The technical challenges were staggering, the timeline impossible, but the scientific payoff would be transformational. The discussion revealed both our capabilities and limitations in stark detail. The velocity problem was fundamental. 3I/ATLAS moved at 130,000 miles per hour. To intercept it, a spacecraft would need to match this speed and direction. Our fastest spacecraft barely reached 40,000 miles per hour. The energy required exceeded our best rockets by factors of 5 or more. Chemical propulsion simply couldn't do it. The timeline was equally challenging. By the time 3I/ATLAS was discovered, it was already months from perihelion. Building and launching a mission typically takes years or decades. We had weeks. Even an emergency response using existing hardware would take too long. The visitor would be gone before any spacecraft could launch. But engineers love impossible challenges. Several teams proposed creative solutions. Use Jupiter's gravity for acceleration. Deploy solar sails for continuous thrust. Chain multiple gravity assists from different planets. Each proposal pushed the boundaries of orbital mechanics. None quite worked, but they showed remarkable ingenuity. The most realistic option involved spacecraft already in flight. The Psyche mission, launched to study a metal asteroid, would pass within 0.3 astronomical units of 3I/ATLAS. With trajectory adjustment, it might achieve a distant flyby. Not ideal, but better than nothing. The proposal required immediate decision and perfect execution. Juno at Jupiter offered another possibility. Using the giant planet's gravity, Juno could theoretically redirect toward 3I/ATLAS. The maneuver would end Juno's Jupiter mission, but provide humanity's only close encounter with an interstellar visitor. The trade-off sparked heated debate about scientific priorities. The propulsion requirements drove technology discussions. Nuclear rockets might provide enough thrust. Solar sails could use radiation pressure for acceleration. Ion drives offered efficiency, but not enough power. Each technology had advocates, but none could meet the immediate need. We were decades from the necessary capabilities. Even if propulsion was solved, other challenges remained. Navigation to a fast-moving target required unprecedented precision. Communication delays meant autonomous operation. Instruments would need to function during a high-speed flyby lasting seconds. Power systems must survive years in deep space. Every subsystem pushed beyond current limits. The scientific instruments posed their own puzzles. What do you measure during a brief encounter? How do you sample material from a potentially active comet? Can you determine composition in seconds? The instrument package would need to be revolutionary. Fast, sensitive, and capable of making decisions without human input. Mission cost estimates ranged from hundreds of millions to billions of dollars. Who would pay? International cooperation seemed essential, but coordination would take time we didn't have. Commercial partnerships might help, but profit motives were unclear. The economics were as challenging as the engineering. The missed opportunity was frustrating. If we'd detected 3I/ATLAS years earlier, a mission might have been possible. If we had interception capabilities ready, we could have launched immediately. The visitor exposed our lack of preparation for such encounters. We needed standing capability for rapid response to cosmic opportunities. Future mission concepts emerged from the discussion. Station a spacecraft at Earth-Sun L2, ready to intercept. Develop modular designs for quick assembly. Create international frameworks for emergency missions. Build propulsion systems capable of extreme velocities. The next interstellar visitor would find us better prepared. The impossibility of reaching 3I/ATLAS taught valuable lessons. We learned our technological limits precisely. We identified the developments needed for future success. We practiced rapid mission planning under extreme constraints. Even failure advanced our capabilities. The impossible mission wasn't wasted effort. The Vera Rubin Observatory was about to change everything. Under construction in Chile, this revolutionary telescope would begin operations just as 3I/ATLAS departed. Its capabilities promised to transform interstellar object science from rare discoveries to routine observations. The age of statistical understanding was beginning. Rubin's specifications were staggering. An 8.4-meter mirror coupled with a 3.2 gigapixel camera. It would photograph the entire visible sky every 3 nights. The sensitivity could detect objects far fainter than current surveys. The field of view was enormous, covering 40 full moons in a single image. This wasn't just an upgrade, it was a revolution. Predictions suggested Rubin would find 10 to 70 interstellar objects annually. The uncertainty reflected our ignorance about the true population, but even the conservative estimate meant a tenfold increase in discoveries. We'd go from 3 objects in 8 years to dozens every year. The sample size would finally enable real statistics. The early detection capability was crucial. Rubin could spot interstellar visitors years before they reached perihelion. This provided time for detailed study and even mission planning. No more scrambling to observe objects already departing. We'd have months or years of lead time. The entire observation paradigm would change. Data volume from Rubin would be unprecedented. 20 terabytes per night, every night, for 10 years. That's roughly 60 petabytes total. Processing this data required new algorithms and massive computing infrastructure. Machine learning would identify candidates from millions of detected objects. Humans couldn't possibly review everything manually. The statistical revolution would answer fundamental questions. What's the true size distribution? How common are different compositions? Do certain approach directions dominate? Are there seasonal variations? With dozens of objects, patterns would emerge. We'd understand the population, not just individuals. Chemical diversity studies would flourish. Each new visitor would add to our catalogue of compositions. We'd learn which chemistries were common and which were rare. The relationship between composition and origin might become clear. 3I/ATLAS's CO, 2 dominants might prove typical or extraordinary. Only statistics would tell. Rubin would enable population dynamic studies. How many objects enter our solar system annually? What fraction comes from recent ejections versus ancient wanderers? How does the interstellar population connect to planetary formation rates? These questions required large samples that Rubin would provide. The alert system would revolutionize response capabilities. Within minutes of detection, Rubin would alert other observatories worldwide. Automated systems would begin follow-up observations immediately. The global response that took days for 3I/ATLAS would happen in hours. Some telescopes might observe new visitors before humans even knew about them. International cooperation frameworks were evolving in preparation. Data sharing agreements ensured global access. Observation coordination protocols were established. Naming conventions were standardized. The infrastructure for managing dozens of annual discoveries was being built. The community was preparing for the flood. Mission planning would become routine. With years of warning, spacecraft interception might be feasible. Not for every object, but for some. We could maintain ready capabilities and launch when opportunities arose. The Comet Interceptor mission, planned for 2029, represented this new philosophy. Wait prepared, then act quickly. Educational impacts would be significant. Students would study dozens of interstellar objects during their education. Each would provide unique lessons about planetary formation. Textbooks would need annual updates. The curriculum would become dynamic, incorporating new discoveries continuously. Learning would mirror the pace of discovery. Public engagement would evolve too. Instead of rare, spectacular events, interstellar visitors would become regular news. The mystery might fade, replaced by familiarity, or perhaps each new discovery would maintain excitement. The diversity revealed by Rubin might keep surprising us indefinitely. The future was approaching rapidly. Soon, 3I/ATLAS would be just one entry in a growing catalogue. Its mysteries might be solved by comparing with similar objects, or it might remain unique even among hundreds of discoveries. As 3I/ATLAS faded into the cosmic distance, we could finally assess what this remarkable visitor had taught us. The lessons extended far beyond chemistry and orbits. This interstellar wanderer had fundamentally changed our perspective on planetary systems, comet formation, and our place in the galaxy. The most profound lesson was about diversity. Our solar system isn't a template for the universe. Other stars create different objects with exotic compositions. CO2-dominated comets can exist. Water doesn't always dominate. The galaxy's chemistry cookbook has recipes we never imagined. Every assumption based on local examples needs reconsideration. We learned that formation environments vary dramatically. The conditions that created 3I/ATLAS don't exist in our solar system. Different stellar types, disk compositions, and thermal structures produce different kinds of comets. The universe experiments with planetary formation in ways that challenge our Earth-centric theories. Nature is more creative than we expected. The survival capabilities of small bodies exceeded our models. 3I/ATLAS endured billions of years in interstellar space. It survived radiation doses that should destroy ice. It maintained structure through temperature extremes and cosmic impacts. The mechanisms that preserve objects across galactic time need better understanding. We underestimated nature's ability to preserve ancient artifacts. Our observational capabilities proved both impressive and limited. We could track objects at hyperbolic velocities and analyze chemistry from millions of miles away. But fundamental properties like size and rotation remained uncertain. Technology pushed to its limits revealed what we can and cannot determine remotely. Every success highlighted remaining limitations. International cooperation worked remarkably well. The global response to 3I/ATLAS showed that humanity could unite around cosmic mysteries. Data sharing was immediate and open. Telescope time was allocated collaboratively. National boundaries disappeared in the face of interstellar science. When the universe presents opportunities, we can work together. The importance of rapid response became clear. Interstellar visitors don't wait for committee meetings and funding cycles. We need standing capabilities for immediate action. The infrastructure for time-domain astronomy requires continuous readiness. Opportunities lasting months can't be captured by systems requiring years of planning. We discovered that impossible chemistry was possible. The CO2 cloud larger than planetary orbits challenged our physics. Activity at distances where comets should be dormant expanded our models. Every anomaly forced us to reconsider what's physically plausible. The universe operates on scales that humble our theories. The galaxy is more connected than we realized. Interstellar objects represent material exchange between star systems. Over cosmic time, significant mass might transfer this way. Planetary systems aren't isolated. They share material through wandering objects. The galaxy slowly mixes its contents across impossible distances. Preparation matters more than prediction. We couldn't have predicted 3I/ATLAS's properties, but we could prepare to study them. Flexible observation strategies beat rigid plans. Adaptability trumped assumptions. The next visitor will surprise us too, but we'll be more ready to be surprised. The universe keeps its deepest secrets well hidden. Despite months of intensive study, 3I/ATLAS remained mysterious. We never determined its exact size, rotation, or internal structure. Some questions can't be answered remotely. Mystery isn't failure, it's motivation for better tools and techniques. Time pressure shapes everything in astronomy. We had months to study something that existed for billions of years. The brief intersection of human curiosity and cosmic phenomena defines our science. We're always racing against orbital mechanics and fading signals. Every observation is precious because it can't be repeated. Finally, we learned that the cosmos is far stranger than we imagined. If 3 interstellar visitors could be so different, what other surprises await? The universe has barely begun showing us its diversity. Each new discovery reveals how much we don't know. That's not discouraging, it's exciting. The cosmos keeps surprising us, and that's exactly